So continue with the respiratory system, internal respiration. So this is the capillary gas exchange in the tissues. And it's the same as external respiration, that it's driven by the partial pressure gradients. It just is in reverse to what happens in the lungs. So the partial pressure in tissue is lower than in arterial blood because you're using the oxygen to make ATP aerobically. The byproduct of that is carbon dioxide. So in the tissues, the carbon dioxide partial pressures in the tissue, interstitial fluid, is high. It's low in the arterial blood because you have lowered it when you exhaled. So the gas exchange happens there. So the partial pressure of oxygen is decreases because it gives the oxygen to the tissues, and so it goes from about 104 down to about 40. The partial pressure of carbon dioxide goes up from about 40 to about 45. And this is just the chart of that. Okay, so how do we move this stuff? It moves in the blood. Oxygen gets transported, carbon dioxide gets transported, along with other things in the blood, but this is what we're looking at with relation to the respiratory system. Okay, so oxygen, a little bit gets dissolved in plasma, but 1.5%, hardly any, is dissolved in plasma. 98.5% of it is bound to the hemoglobin, and it's the heme that it's bound to. If you remember, each hemoglobin molecule has 4 iron atoms in it, and 1 oxygen binds to each iron. So you have 4 O2s per hemoglobin. And so the hemoglobin of the red blood cells is what transports the oxygen. Hardly any of it is dissolved in plasma. But if you take that little bit out of the plasma through diffusion, then some leaves the hemoglobin to go into the plasma, and then that leaves. So it's kind of a chain reaction there. So oxyhemoglobin has it, and reduced has less than 4. Now, what's interesting is the affinity for oxygen in hemoglobin. So the loading and unloading of hemoglobin is facilitated by the hemoglobin itself. So as oxygen binds, the affinity for oxygen increases, and as oxygen is released, the affinity for oxygen decreases. So what that means is that when the hemoglobin gets to an oxygen-rich environment and oxygen goes onto it, then it wants more, and it's better at grabbing oxygen from the oxygen-rich environment. When the hemoglobin gets to an oxygen-poor environment and some of the oxygen is released because of the partial pressure gradient, then the hemoglobin holds on to the next oxygen less and will give it up easier. So it's really suited for these exchanges because at the lungs, the affinity increases the more oxygen there is, and at the tissues, the less oxygen there is, the affinity decreases, and it gives up the oxygen easier in the tissues that need it the most. There are 4 oxygens in a fully saturated hemoglobin. Partially saturated is when you have less than 4. Other things change the rate of loading and unloading. So the partial pressure of oxygen is the one we just talked about, but temperature is also a big deal. In warmer tissues, there's less affinity for oxygen in warmer conditions. So cool oxygen wants to dissolve and go into the blood. In warm, it wants to come out of the blood. It's like you put a pot of water on a stove, and as the water heats up, bubbles form and gases leave, because gases are less soluble in warm liquids than in cool liquids. So which is opposite to solids. So warm, oxygen wants to leave the blood. And that's useful because if you're using muscles, those muscles will be warm, and they will also be low in oxygen, so that low partial pressure of oxygen and the increased temperature means that that muscle will get more oxygen. If you're on the Stairmaster, your gluteus maximus will get lots of oxygen. If you're playing PlayStation and not using your glutes, there's not going to be as much exchange. pH is a big thing. So as pH becomes more acidic, then oxygen leaves easier. So if there's lactic acid, so the tissues are anaerobic, oxygen will leave very well. So alkaline, it holds on to the oxygen. Acidic, it gives up the oxygen better. The partial pressure of CO2 works the opposite of the partial pressure of oxygen. So the more CO2 there is, the CO2 will bind to the globin of the hemoglobin, we'll see, and then that makes the affinity for oxygen less, so more oxygen will leave. It's easier for the oxygen to leave if the presence of carbon dioxide is high, again, metabolically active tissue. And the last thing is there's a chemical called BPG, and BPG is produced in metabolically active tissues. It's actually carried in the blood, but it's activated in metabolically active tissues, and that facilitates the oxygen leaving the blood. It works the opposite in the lungs. So the lungs are cooler, have a higher partial pressure of oxygen, tend to be a little on the alkaline side, have less CO2, which is why it's a little on the alkaline side, and the BPG is different. So load oxygen happens at the lungs, unload oxygen happens at metabolically active tissues. So we can look at a curve, and we end up with an S-shaped curve, which is this, so that if exercising tissues, it's very easy, and in the lungs, it wants to load. So it's very easy to unload, hard to unload, very easy to load at this end. That's the oxygen saturation is causing that. The other things will shift that to the right. So if the partial pressure of oxygen is about 100, then we're about 98% saturated. And that's what the oximeter thing that they put on your fingernail is about. Once you're 98% saturated, breathing deeper and having augmented oxygen isn't going to increase the binding, hardly at all. In the venous blood, the hemoglobin is usually 75% saturated. It usually gives up 1 oxygen per circuit. That's why you've got about 3 circuits, about 3 minutes before the oxygen gets used up. And so it's completely saturated at a PO2 of 70, whatever. So 20 to 25% is unloaded in one circulation. You will have zero oxygen kind of after 5 minutes. So this is the same curve. Right. So temperature, acidity, partial pressure of CO2 and BPG will shift the whole thing to the right and make it easier to unload. And the tissue is easier to load in the lungs. So this declining pH is called the Bohr effect, and we'll just so heat production increases and decreases the affinity for O2, pH, acidity, Bohr effect, carbon dioxide. Now the amount of carbon dioxide, because carbon dioxide becomes carbonic acid, that lowers the pH. So those things work kind of hand in hand. We're not going to worry about any homeostatic imbalances. So how does carbon dioxide move through? It travels very differently. 7 to 10% is actually dissolved in plasma. It's just CO2 dissolved in plasma, the same as in beer or in Coke. 20% gets bound to the protein part of the hemoglobin, not to the heme part. And 70% of it undergoes a chemical reaction with the water molecules and becomes bicarbonate ions. So if we look at it, CO2 plus H2O becomes H2CO3, carbonic acid, which is going to dissociate into H plus and HCO3 minus. Now, when we are going to talk about fluid electrolyte acid base, in that unit, we will talk a lot more about this. But it works out that 70% is this, 10% is this, and the remaining 20% is attached to the hemoglobin. So I'm not going to get into it, but we have this chloride shift. What happens is by concentration gradients, the HCO3 minus moves, and like you can follow this if you want. I'm not going to expect you to memorize this, but really what happens is in the pulmonary capillaries it goes one way, and it means that carbon dioxide ends up diffusing out into the alveoli, and at the systemic capillaries it goes the other. Now, the Haldane effect is the amount of carbon dioxide transported is affected by the partial pressure of oxygen. The lower the partial pressure of oxygen, the more CO2 can be carried, so it finds that balance. So as the tissues, more carbon dioxide enters, that means more oxygen dissociates, and as the hemoglobin releases oxygen, the hemoglobin will pick up carbon dioxide better. So these two things enhance the exchange. We're going to talk about the effects of carbon dioxide on blood pH in an entirely separate chapter, so I'm not spending any time on it now. The last thing we're going to talk about is controlling respiration, controlling rates of breathing. So this happens in the brainstem, in the medulla oblongata and the pons. there are different groups of neurons that control it. So the dorsal respiratory group is on the back of the medulla oblongata, and it takes input from the stretch and the chemoreceptors. So it's looking at how much the lungs are stretching and what is the chemical composition of the blood. How much oxygen is there? What's the pH of the blood? And it tries to arrange your breathing patterns to normalize those two things. The ventral group on the front of the medulla sets the rhythm, the 12 to 15 breaths a minute. It excites the inspiratory muscles. It works through the phrenic nerve, and so what happens is it turns on the inspiratory muscles. You breathe in, and then it turns on the expiratory neurons, which then inhibit the inspiratory neurons, and you relax and you breathe out. So the dorsal respiratory group is here, the ventral respiratory group is here, and they control the base rate of breathing. Now, in the pons, there is a group. It's called the Pontine centers. What they do is they modify the activity of the ventral group. So the ventral group will set the pace. But the pons will make it speed up or slow down and smooth out the transitions between, kind of depending on what's necessary and what's going to happen. The respiratory rhythm is some sort of reciprocal inhibition. One, when you're breathing in, you're inhibiting breathing out, and when you're breathing out, you're inhibiting breathing in, fundamentally. So the depth and rate. The depth is determined by how actively the respiratory muscles are stimulated by the respiratory center. So lots of stimulation in all the intercostals and the diaphragm and the serratus posterior, superior, and the scalene muscles, and all of these accessory muscles are all excited at the same time. You'll take a deep breath. If it's hardly any, it's just the diaphragm, you'll take a shallow breath. The rate is how long the inspiration is active. And they're modified in response to changing body demand. So if you start to run and the carbon dioxide levels start to go up, then the depth and rate of breathing is going to automatically change to counteract that. And it really is the amount of carbon dioxide that is the biggest influence on this. So it's not a lack of oxygen that makes you breathe. It's a buildup of carbon dioxide. So if PCO2, so the partial pressure of carbon dioxide levels rise, which is called hypercapnia, the carbon dioxide accumulates in the brain, which makes the pH go down. The increased number of hydrogen ions as pH goes down stimulates the chemoreceptors of the brainstem, which then increases the depth and rate of breathing to try and blow off this carbon dioxide. It is the largest influence is that. So arterial PCO2 will really affect that. Now, if you hyperventilate and you blow off too much CO2, you will end up with apnea. You will end up with breathing slowing down, if not stopping. So if you hyperventilate, you will stop. What this really means is that when people, so you want to learn to free dive, you want to swim underwater. the conventional logic is that you take as deep a breath as possible to get as much oxygen as possible. When your blood level is saturated, then you're not going to get any more oxygen in the blood. The blood will unload about 20% of it on a circuit, and you think, well, if I have more oxygen still in my lungs, then it will. But as soon as that PCO2 or that PO2 drops below 100, you're not going to get full saturation. However, the amount of carbon dioxide levels will go up, which will be affecting the respiratory centers in your brain and telling you you need to breathe. So within a few seconds, it's the rising amount of carbon dioxide rather than the lowering the amount of oxygen that matters. You've got enough oxygen in your blood for 3 or 4 minutes of gas exchange. But the carbon dioxide levels go up. So really what you want to do is saturate your blood by some deep, shallow, or deep, slow breathing. And then, as you're staying underwater, you exhale, you blow out the carbon dioxide, and then that carbon dioxide levels doesn't build up, causing your respiratory centers to want you to take a breath. The influence of low partial pressure of oxygen, it's got to be really low. It's got to drop to 60 millimeters of mercury to stimulate increased ventilation. So you got a couple of minutes before it's going to drop. Well, at least 2 minutes before it drops that low. So it's the carbon dioxide is the much stronger thing. So this is just a chart looking at the carotid bodies where this stuff all gets monitored. So arterial pH will change this, and again, when we do the acid-base unit, we will talk more about it. So rising carbon dioxide levels are the most powerful respiratory stimulus. Lowering oxygen levels is only indirect and is almost secondary. It has to drop below 60 mils of mercury before it becomes the major stimulus. Any changes in pH, including metabolic factors like lactic acid, will change that and make you breathe more. You can also override this with higher brain centers. So you can tell yourself in your cerebral cortex to hold the breath, and you will. So those are cortical controls. Pain and anger and fear will modify the rate and depth of breathing, and that's because of the limbic system affecting the hypothalamus, which is going to affect the respiratory centers. We have these irritant reflexes, which are important to understand asthma, but there are receptors in the bronchioles that respond to irritating things, and it will promote constriction of air passages. It'll make you cough, it'll make you sneeze, or if it's deep in the lungs, it will make you constrict and stop the passage of air with those irritants. And that's what happens with people with asthma. These irritant reflexes are too strong. There's something called the Herring-Brewer reflex. And what this is saying is that the more your lungs are expanded, the stretch receptors in the walls of the lungs inhibit the breathing centers. So as you fill your lungs, it gets harder and harder and harder to put more air in your lungs until you can't fill to the point where you can damage the lungs. It's a protective response. It just stops you from over-inhaling. This is kind of a summation of that. So when you start to work out, the receptors in the muscles and joints positively affect, so you are breathing deeper even before you have the need for the oxygen, because the muscles are working and will be needing oxygen in a second. Chemoreceptors, looking at pH and carbon dioxide levels, will make you breathe more to get rid of it. That's the strongest one. The peripheral receptors are looking at doing the exact same thing. Pain and other stimulus will affect, which will then affect the centers, which are thinking about it, right? Stretch receptors inhibit, irritant receptors inhibit.